All right, hi folks, and today I want to go over some of the things that I've seen as you've been bringing in some of your trusses and address some of the questions that I've been receiving from people both in during the lab and in email. And one of the things I've noticed is that in your quest to build a fancy truss, you're maybe starting off too fancy and not looking at some of the fundamentals and the basics and the hand calculations that we spent the early part of the year working on. And this is something that's a lot easier to address when we're doing this in person on a day in, day out basis, and we're talking on campus every day. And so it's a challenge adapting this project to our current COVID circumstances, and I appreciate your efforts in making this happen. So I just want to go through and say I've taken a look at some trusses, and some people have these factors into their truss and have thought this through. There might be one or two things in here that you don't necessarily have thought of, and that for some people it might be, oh, that's what he meant. And if that's the case, then I'm sorry, it's just coming through to you right now. But anyway, we're going to take a look at JFMatrix, which I mentioned earlier in the year when we were doing hand calculations and our first complex truss calculations as a way to go and check your solutions. And I have to admit, it's not the greatest piece of software. It's just the best that's available right now. For a long time, there was a really great app from Autodesk. They took it off the market because their analysis had gone elsewhere, but they never really brought that functionality back. And I keep hoping to see something that's as user friendly as what the heck was the name of it anyways? Force Effect was the name of their app. And it would be great to have something as user friendly and um, suitable for this type of analysis as Force Effect was. It was a real pain when that disappeared. But JFMatrix is free, and I appreciate the hard work that the programmers have put into that and the investment that they're making in keeping their website up and running. I don't want to, when I say it's not great, I'm not the one paying for it. So I'm grateful for it because when I go out there and look, it's the best that I've been able to find to recommend. And I usually spend a couple hours each year online trying to find something better. And for what we're doing, it's pretty darn good. So I'll use that and I'll talk a little bit more about JFMatrix when we get to it. But I do want to talk a few things about the overall structure of your truss and what we're looking for in designs. And I've seen some interesting designs come forward, and in some of them, I've been looking at them saying, okay, this is somebody who knows about building roof trusses or bridge trusses, and you're thinking, oh, I'm going to build it like I built my West Point Bridge Designer truss, but you haven't actually picked out the fact that this is actually a very simplified loading condition that we've got in our truss challenge, okay? Because a general purpose truss, so a roof truss or even bridge trusses, they're designed to support evenly distributed loads. So, if you think about a roof, it could be subject to snow loading, okay? And it's going to be weighed evenly all the way across the roof. Okay, our truss is going to have like one point. There's only one node that load is ever put on in our truss, and that's not a normal situation for for a truss. For instance, the Portman Bridge, that's a giant, humongous truss, and when you build giant, humongous trusses, the dead load, the weight of the structure itself becomes so great in relation to the live load, the weight of the cars or people going across there, that really the live load almost becomes insignificant. That gets flipped around with our design. So in our case, the weight of the trusses itself is going to be 75 grams, and I'm hoping that we're holding like 10 kilograms or more when we put the weight on it. So the weight of the truss is the insignificant part. So we've kind of flipped that around from these massive bridges, and we're building a lighter, smaller structure. And as the nature of scaling things goes, um, it's gonna be a little different. Actually, just a brief aside, when you think about scaling things, um, and why we don't have giant robots wandering the planet. Think if you scaled a human and said, okay, Jason, I'm going to make you twice as big. So that would mean that my height would go up by a factor of 2, my width would go up by a factor of 2, and my thickness would go up by a factor of 2. I would weigh 8 times as much. Catch is, my leg bones that have to support 8 times the weight, they would have doubled in length, but that doesn't help their strength. As we know from column buckling, that actually makes them 4 times weaker. They would only have increased in width and in thickness. So they would have increased their cross-sectional area only by a factor of 4, even though my weight had increased by a factor of 8. So eventually, as you start scaling people up, okay, um, you're going to run into a problem where the mass increase becomes too great for the cross-sectional area increase to be able to support those loads. And we actually see this in reality when you look at the difference between competition weightlifters, the big heavyweight weightlifters, the strongman competitors, and gymnasts. Okay, different people designed to do different things. And the ability of the gymnast to spring and bounce and their power to weight ratio is really good because they're small and they've got a low mass relative to their cross-sectional area of muscle and bones. Whereas these giant power lifters, their power is insane, but their power to weight ratio isn't so good, so they don't bounce around quite like gymnasts. Um, it would be freaky if they did. Okay, anyways, that was just a little aside to think about why we don't have giants roaming the planet. But it does relate to our truss because our truss is small, like the gymnast, not huge, like the Portman Bridge slash power lifter. Okay, now our truss is also greatly simplified so that we can analyze the forces relative to loading. So because we've got the load in one place, that means that we're probably going to have the thickest part of the truss in one place too. Because when you look at a general purpose truss, okay, where you've got evenly distributed load, either because of the weight of the truss itself or a snow load, or because you simply don't know where that load is going to be applied at any one time. So for instance, in West Point Bridge Designer, your truck rolled across the bridge and it tested this node and this node and this node and this node and this node, and it could fail in any one of those situations. We don't want to test 8 different loading positions. That would just be additional calculation. I've tried to keep it nice and simple. Okay, um, so don't go looking maybe at your standard roof truss where its tallest point is in the middle, because if you've got the tallest point in the middle or your West Point Bridge Designer had the tallest point in the middle, those are great designs, but for evenly loaded trusses. Okay, so maybe look something at the Johnson Street Bridge, where now you're starting to get into something cantilevered, and you can see on the Johnson Street Bridge that the thickest point is not at the middle. The thickest point is over here, where the greatest bending moment is about to occur, because by the time they get that truss down and it's in position, this end is being supported out here, and you know, you've got a different load situation than when this is up in the air, and all of that force, all of that weight has to be supported back down here. Okay, um, so generally what we're wanting to do is we're wanting to put the tallest point, the thickest point of the truss, right above the load. And what we call in engineering, we say this is where the greatest bending moment is, where your greatest twisting force is going to be located. And a good example of a truss that's somewhat similar to what we're going to be working on is the cranes down at the Port of Vancouver, these gantry cranes right in here. They come over here and they have to be able to pick a container up off the ship right here and then bring it right in here and drop it down, but they have to be able to reach out over top of the container ship. So you can see right here at the end of the truss right in here, they've got support right in here, and that support is bolted into the ground because otherwise your whole crane would just tilt this way into the ocean. I think actually happened once. It wasn't good. We've got a vertical support coming up here. Now you can see in here, big, thick, solid columns, okay? And they make that cross-sectional area huge so that they can have a high moment of inertia. They make those round, okay? You can see this is different right here. These members are cylindrical, round in cross-section, because they are going to be loaded in compression and have things pushing down on them. So they're trying to fight buckling. And with buckling, you never know which way it's going to pop out. So you make basically your moment of inertia the same in all directions. So this is being supported up right here. And then we've got a force coming down right over here. Well, if you think about that, that is almost the same as our loading conditions for our truss, except we've got the support point right here and the support point right here. So flip those forces around and now they're pointing upwards. And in the middle right here, instead of having a force pointing upwards, you've got a force pointing downwards right here. So it's basically you're building the top part of a crane for the port, okay, but in the opposite direction. And as a result, this gives us a good idea maybe of how we want to take a look at our truss. Picture that in cross section, and you can see that right where that maximum moment of upwards force is going, we've got the thickest, tallest part of that truss, the most resistant part to bending. And in our case, it'll be where that load's pulling it downwards. We want to have our thickest, tallest part of the truss most resistant to bending. Okay, so we're going to use that as a starting point, and I've picked something simple right here to start us off. Now, this is in JFMatrix, and I just want to whip back over here because I know I talked briefly about this in the past, but I'm just going to switch over to my web browser right here, and let me just bring up a new window, and you can get to JFMatrix just by typing in jfmatrix.com. And you come to this website right here, and you can scroll down right here. Now it does different types of analysis. Make sure you click on the truss analysis. Okay, and when I started up, it comes up with the last truss that I organized. I'm just going to tell it I want a new model. And yes, away it goes. It popped up an ad on my other screen over here. I'm just going to get rid of that. So um, anyway, here we go. And to create your truss, you just come in here and you draw some joints. Okay, and right in here, you can zoom in, zoom out, but 1, 2, 3. Okay, now these are our fixed trusses. They all have positions that we know, so you can come in here and you can go edit, and under edit, you're going to edit the joint coordinates, click on truss number 1, and I'm going to put that at 0, 0. Okay, so there's our first truss over there. That's going to be on the long end out there getting support. And then you can edit your coordinates right here. And this one will be at 400 millimeters, but just to simplify everything on here, I'm just going to put it in a position of 4, okay? Because we're just using this to analyze the forces. So long as all of our proportions are okay, we'll be fine. So I'll set that at 4, and the y coordinate, the vertical coordinate, I'll set to 0. And at some point in here, you may see that go off your screen, and you might have to zoom in or zoom out or use the little hand icon up here to move things back in. And so we started at 0, 0. We came over to 4, 0. And just like in your AutoCAD drawing, the next one is 15 centimeters over here. So this is going to be at 5.5, comma 0. And there's our 3 basic nodes right in there. And so we're going to have a force coming down on this one and force as securing these in place. So it's going to push upwards. Let's add one more node right here since we're in node mode. Come right over there. And let's just edit that joint coordinate to see where we want it to go. That's at position 4, which is perfect, 400 millimeters over because it lines it up there. And it's 100 millimeters up. That looks good to me, okay, as a starting point. Keep in mind that every one of these nodes has to be at least 70 millimeters, or in the way we're setting this up, 0.7, 70 millimeters apart from each other. So you've got some nodes in there. Now you can draw some beams, they call them, members, I call them. Click on one and just bring it over to the next one, the next one, the next one, the next one, and it tells you member numbers for each. Hit escape when you're done doing that, and then draw the next one. Comes right in there, and hit escape again. And now you've got a simple truss drawn up in here. Add your supports, and we'll put a roller support in the, oh, just a minute, I want to add a roll. Got to click OK and then click right there. There's a roller support right there, and that's in the Y direction, so it can't roll anywhere. And add a pin support or a hinge support, as they call it. Click OK and put it right down there. And then draw joint loads. So we're going to put a load. In this case, I'm just going to say minus 10 newtons. It's going to calculate it in kilonewtons, but whatever. There we go. Like I say, this is all just relative. So long as you scale everything up and scale everything down, you're going to be fine. And so now you can go ahead and create a structure in right here. Keep in mind, we're analyzing as a truss structure. When you click Run Analysis, it will take you over here and you'll see that the members, I'm pointing at the screen here, I'm sure that helps you, the members up top change, and you're in your results mode. And when you click on that, that gives you the compressive and tensile forces in each member. Okay, so here I've got 13.1, 11.24. They're red, they're in compression. No wonder right here I've got 10 newtons coming down. Okay, I know it says kilonewtons, just ignore the kilo. It all cancels out. Here I've got 11 newtons in tension, so these ones are all in tension. That's because I've got a weight pulling down right here. There is no way that these two horizontal members can support anything vertically, so all of my force has to go up here, and then it gets distributed out between these two members. So that works pretty good. Now, if you want to come back and change something, okay, there's other things that you can do on here. You can take a look at the deflected diagram, which is a bit exaggerated right on here. You can animate it so you can see how it goes. That's a nice feature. And you can view reports so you can get the length of each member. And this actually does handle cross sections, and it can do more than we're using it for. But what we're using it for is enough. Now, if you want to go back and edit it, you click Unlock Model. Now, the only thing, okay, that makes me say, anything other than perfectly wonderful things about JFMatrix, because it is a nice asset to have available to us, especially for free. We do appreciate that. Just in case anyone from JFMatrix is listening, thank you. Been using this for a couple of years now. We can't just click on this node and drag it to a new position. It's probably harder to do in a JavaScript thing or whatever programming language this is written in than I give it credit for. What we have to do is we have to come in here and we go Edit Joint Coordinates. And so if you want to try that truss with a different coordinate, you click on that and say, well, I was at a height of 1, maybe at 12 centimeters up. It will work better. So I type in 1.2 and the truss changes right like that. So yeah, not drag and drop. You can't just drag it around. You do have to go in and edit the nodes, which is a lot better than a lot of truss editors where you have to go in and actually change them in a separate text file. Run your analysis right here, and what you'd expect to see, we want, where are we right there? A is, this force is going to remain the same. Our reaction force at the two ends remains the same. This will always be 73% of your load. This will always be 27% of your load, just because of the ratio of the distances between here and here. Okay, but because we made this taller, now we should see a slightly reduced force in compression right here, because since this member is taller, this side of the triangle is taller. So when we're calculating our horizontal component of the vector, and you can see the horizontal number appearing right down here, okay, since this side is taller, our 10 newtons relative to that side will result in a smaller number right down here. Okay, in other words, we're minimizing the effect of the horizontal component. So that's a quick intro into what's going on in JFMatrix. Now you can try registering for an account. I haven't been able to get that to work for me, and if you register for an account, then you can save your file to your account on the cloud. And it did work a year or so ago. It's not working right now. So what I recommend that you do is if you get a particularly interesting result, you take a screenshot and you record where your nodes are. Okay, so here's some images that I've captured from JFMatrix, and I've put the node locations in here so you can recreate similar results. And I just went through and I punched in simple truss like you saw right there. And like I say, I'm starting out simple because I want to understand where the forces are going and I want to think, what is each member doing? Don't want you just going and drawing a structure unless you can tell me what you think each member of that truss is going to be doing. And I should probably come around in the lab and say, why did you put that there? Okay, so we tried one and we recorded the results. You can see 17 newtons right there, 15 newtons right there. I also went through and did a little bit of Pythagoras to calculate the length right here because of course the length of your truss members matters, particularly if they're loaded in compression. Okay, then I came in here and tried a different height, just like I showed you how to do that. And now I came through. JFMatrix did do the calculation for the member lengths, and you can find that in the report. I found it a heck of a lot easier once I'd recorded the node locations to do, oh, well, this is 150 millimeters, this is 140 millimeters, a squared plus b squared equals c squared, 205 millimeters. Okay, just expressed it in our JFMatrix terms there. Now, this is where things get interesting, is after you've done that analysis, it's time to compare the results and dig in and find out what that means, okay? Because what we're trying to do is we're trying to make a strong truss, but we're subject to weight limits. And we're also subject to thickness limits on each of our members because we're working from the medium density fiberboard. Now, something we know is that the compressive member strength decreases with length squared. That's a column buckling thing. We've done a couple labs on column buckling. We've looked at that. If you make something half the length, okay, it's twice as strong. If you make it twice the length, it's 1/4 the strength. Okay, now the other advantage to keeping things short when we're dealing with a limited length is that you've got less material there too. So if you've got something that's shorter, okay, and the same weight, well, you can make it thicker, which makes it stronger. Or not thicker in our case, I guess higher. You can increase the cross section. That's why I chose to use those words. All right, now let's take a look at this member right up here, okay, the top left member here, and you can go back to the previous slides if you can't quite see the numbers on this slide to see what I'm talking from, but the original length using Pythagoras of this member in red right here was 406 millimeters. And then when we increased the height, our new length, because it had to reach a little bit further up here, was 424 millimeters. So we can calculate the relative strength of this new member to the original member because we can say, well, let's just take a relative length and square it. So the old member was 406 millimeters. The new member is 424, okay? Square that, and you get the new member right in here is 0.917 times as strong as the old member right up here. Okay, so now what does that mean? Well, go and take a look at what your original load was. And our original load was 15.8 newtons because it had a high horizontal component in there. And you'll notice that our tensile members down here were pretty stressed too. By increasing the height, we really reduced the horizontal component of the load. In fact, it dropped it from 15 newtons down to 8, basically 52% of the original load. So by making this taller and making this top member longer, yes, the top member got a little bit weaker, but because the length didn't change all that much, because really the length in this one is being determined by this long piece right down here, okay? This is still relatively insignificant until it starts getting quite a bit longer. Our length was our length resulted in a reduction to 92, I guess, percent of the strength, but the load that we gained as a result was a reduction to 52%. So in other words, on this side of the truss, at least, much stronger. Okay, this is a way better configuration for resisting buckling because we don't have nearly as much horizontal force in there. Okay, the horizontal component's greatly reduced. So this is great. We made the truss taller. We put that tallest section right over top of where the load is being applied, and obviously taller is better. Now, and it's better because it's minimizing the horizontal component of force. However, we do have some limitations. We're limited by the size of the hardboard sheet, obviously. So, we're working from well, 24 by 18 in Imperial, I think is like 600 by 400 in metric sheet. And so you've got to get two members out of there. So obviously you can't go all the way up. You've got to fit your triangles in there and tuck them in nicely so that those two members fit. You're limited by mass. Okay, so you can't have an infinitely tall truss member. If it was infinitely tall, you would, essentially only have 10 newtons of force. Your load would come right down into the base. It would be easy peasy. Okay, except your infinitely long members would have zero buckling strength because they're infinitely long. So, well, we can't do infinite. How high can we go? You can sit around and play with it in AutoCAD. You might be able to get 260 millimeters out of it, maybe 270, maybe only 240, depending on how you line things up. I said, let's just throw out a number like 250 millimeter tall truss and see if this gains us any advantage. Okay, so here's my tallest truss. And so by just punching this in, I've got some new dimensions in here. I just edited this one dimension. It's still at 4 or 400 millimeters in the X direction. In this case, 250 millimeters in the Y, or 2.5 in our JFMatrix analysis. And here's our lengths right along here. We've increased the lengths on both these sides, making them somewhat weaker. Okay, but we've also greatly reduced the force in those members. So let's see if this is better than our previous condition. Okay, and so this time I'm going to analyze this side of the truss. When I was doing this for myself, I did both sides both times just to double check and make sure I'm not leading you down a garden path. The results are similar. I'm not hiding anything from you right here. It's just instead of showing you both sides, if I show you one, you know how to do the other side. Okay, so let's take a look at the right-hand compressive member over here. Now, in our previous test, so we started with a really short one, then we did a medium height one. So our previous test here was the medium height one, and we calculated that the length of this red member right over here was 205 millimeters long. And now, when we've increased this length, the length of that member is up to 290 millimeters long. Okay, so this results in a 205 over 290 squared reduction in strength. So this member right here, even if it's got the exact same moment of inertia and same cross section and all of that, is only going to be 50% as strong because it's about 40% longer. Now, our previous load was 10.6 newtons. Our new load has been reduced, okay, but not all that much because we went from being kind of tall to being really tall. So it's only come down to 80% of the load. So if we've reduced our strength by 50%, but only reduced our load by 80%, then this is a worse configuration than we were in before. Okay, so when we were at the lowest truss, it wasn't very good because we had too much horizontal component in our compressive and tensile members. When we were at our medium truss, it was pretty good. But when we go to our tall truss, even though we've reduced the forces because we've reduced the horizontal component as a relative part of the vector, we've really weakened those vertical members because now they're so long in order to do that, that they're just flopping around like wet noodles. So we've got a few things that we've discovered from sitting down and doing this and just walking through right here and taking a look at our heights. So our first test showed us that 140 millimeter truss height is better than 70 millimeters. Our second test showed us that 140 millimeters is also better than 250 millimeters. So somewhere our optimal height for the truss is going to be between 70 millimeters and 250 millimeters using this simple configuration and not taking into account a couple other factors. This is a guide to say, okay, well, when I'm doing this, how tall or, you know, should it be? Super low is not good. Super tall is not really good. Somewhere in there, in the range of heights that you can cut out of your truss is the optimal height for your design. Well, what's that height going to be? Um, well, we've laid out some numbers in here. It's between 70 and 250. So do a comparison. Go back to that truss, edit it up, and see is 120 better than 240 in terms of its resistance to buckling. And if it is, then you know that the optimal height is less than 120. It's somewhere between uh, yeah, so sorry, it's between 120 and 240. If it isn't in there, then you know the optimal height is probably going to be between 140 and 250. So split the difference, try 180 millimeters and see what you get. And if that works, split the difference and keep coming down and pretty close. You don't have to get to the nearest millimeter or anything like that. You just want to get an idea to maybe the nearest centimeter so that you've got a number to start working around. And then you probably want to say, well, if I found pretty much the optimal height without thinking about mass, maybe if I make it just a bit shorter than that, then I can make all my members thicker, and that gets me a bit of an optimal calculation. And honestly, if we had to get it perfect before we went and built the truss, we could run a mathematical calculation calculating the cross-sectional area and factoring that in as well. But this is enough math for today, right? Um, Keep in mind that really, although I've been using JFMatrix to get some pretty pictures with some nice colors in there, you don't have to use JFMatrix. Those were like 3-node triangles. We've done those calculations in class since January. Okay, make sure you do know how to do those by hand, please. We'll be asking you questions about them a little bit later on. Okay, now you've gone through and you've found a height that you like. Now in this case, I haven't gone through and adapted this to the height that I like. I've just gone through and I threw a couple nodes in here. And so I came into JFMatrix and I had to delete this member and delete this member and put a couple new nodes in and bang, 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 calculated what's the intermediate point right on here. If I'm at 0, 0 and 4, comma 2.5, my intermediate point is at 4 divided by 2 and 2.5 divided by 2. So do a little bit of math and you can figure out where to put those nodes so that they're right smack in the middle of the members. Why does it help to have those nodes right smack in the middle of the members? Well, it shortens the length of the member. And with our column buckling, half the length is 4 times the strength. So now we're making these members stronger, which means we can either support more force before they buckle, or we can make them smaller, allowing us to build the truss a little bit lighter. The amount that we reduce the size of the members may compensate for the additional weight of running a dowel across, because each of your nodes has to be connected by a dowel or barbecue skewer to the other side. So that might compensate for the weight of putting that node in there. But really, if we're going to do that, we want to make sure that we maximize what we're doing with each of our members and each of our nodes. And in this case, we've got some zero force members down here. Okay. The zero force member is a little bit of a tricky thing. They have to be there because they are the part that is keeping this section from buckling. Now, the thing about buckling is you're never quite sure, is it going to buckle out this way or is it going to buckle down this way? And when it starts to buckle, that zero force member is no longer a zero force member. Okay, remember we're doing just a linear stress analysis right on here. We're not doing a buckling analysis. Got to go into Fusion 360 to do the buckling analysis. It's a much, much more complex analysis that Fusion 360 runs on there. So as this member starts to go, because it's random right in here, I don't know if that's going to pull out, putting this member into tension, or push in, putting this member into compression. And if I don't know whether the member is going to be in tension or in compression, then I can't just put a skinny tensile member in there that weighs at almost nothing. I have to put something in there that can resist at least a little bit of compression. And I run the risk that if I don't put enough in there, that this is going to start to fail in the inward direction, and poof, this is going to buckle out because I didn't make this strong, and now it's no longer a zero force member because this is trying to buckle down this way. And it would be nice if we could just avoid that, because not only that, if it's zero force member, what's it doing in my structure? Why do I want it there? Well, you're kind of required to have it there if you put a node right here, because that node needs to be held in a statically determinate position. You can't just go randomly throwing nodes into the middle of members. Nodes have a purpose. They have to be joined together. Okay, so how do we deal with that? Well, we control it. And we say, well, if I'd like this to be a tensile member, then I need to make sure that it's going to be loaded in tension. And if I want to make sure that it's going to be loaded in tension, I say, well, what do I do to this node to make sure that it's not going to buckle? Okay, this one right here, to make sure it's not going to buckle. Well, this node, if I move it out a little bit, then the vector right here will be pushing this way, and the vector right here will be pushing up that way. And as you know, if you take my pension statement, if you take a piece of paper like this and it's folded like this, when you push on the ends, it's folding up that way. It's not randomly coming down and folding down that way, okay? Anytime you push on that, if it's pre-bent, it's going up in that direction. Look at my pensions flying away. Anyway, uh, here we go. This is that is one of the beautiful things about teaching. It seems like I started doing this job yesterday, and that statement says I've got 23 years in already. So, um, good things going on with your pensions there, folks. So let's take a look right here, and we'll come down here. And I've moved these up a little bit, just like we had that little pre-bend in the pension statement there from it being in the mail. This is folded up this way. And now, when I pull down on this member right here and push up on this one right here, this is going to try to pop out in this direction. This one's going to try to pop out in that direction. And you can see these two members have now picked up some tensile load. Now that also means that because this one's trying to pop out here and this member's trying to pop out over here, these ones are helping this member right here support this load down below. The other thing that's happened is that this member right in here now sees a reduced load. You can see that says 8.07 newtons right on there. If we go back to our previous structure, okay, 8.48 or something like that. Well, the reason that's changed is because now this is a steeper angle than it used to be. It used to be coming right in here, and because it's steeper, it's got it's more in line with the force, so we've got less horizontal component acting in there. Okay, so those horizontal and vertical components really play a big role in how our stresses are distributed in this structure. Now, this one's being held up right in here. In addition to supporting some of the vertical force, you'll notice that it's pulling off in this direction. So it's also pulling this node over that way, thus reducing some of the tensile force in the bottom. And this one's pulling that way just a little bit, thus reducing some of the tensile force in this bottom member. And here, this one's also gone a little bit steeper. Now, it is a little bit longer. We have to account for that. But anyways, significant changes just with two nodes right on there. So now that you've got this structure, okay, it's pretty easy to go back and edit that just by changing the node locations around in JFMatrix to see what happens as you bring them down lower. And as you play around with their locations, you do start to get some interesting configurations in there. A couple of things to keep in mind. Shorter is better generally as far as your members go. Now, I've put a limit that none of your members can be shorter than 70 millimeters because you've got to have at least 70 millimeters between each of your nodes. Okay. But aside from that, you get a massive increase in buckling resistance. If you can get them right down to 70 millimeters, that's going to be your strongest possible member. You are subject to a 75-gram weight limit for the entire structure. So each time you add a node, you've got a little bit of a weight penalty from because you've got at each node, you have to have a piece of wood, a dowel, or a barbecue skewer. Barbecue skewers are, if you make a hole that's 3 millimeters in diameter, you can run the barbecue skewer across. That's going to be your lightest option for joining two nodes. Some of your more heavily loaded nodes, you might want to go up to a 1/4 inch dowel, which will be about a 6 millimeter diameter hole. Um, but make sure that you're getting every bit of your structure working at 100%. If a member is stronger than it needs to be, then you're wasting weight right there. You can move it over to a member that's more stressed, make it a little bit stronger. And the whole goal is that if you've got a perfectly designed truss right here, when you put the weight on it, you're going to keep it loading everything all up at once, and it's all going to fail at the exact same time. Now, that would be the perfect situation, perfectly equally distributed force, um, and that should result in your maximum support. But as much as we set this up as a competition and want you to build a competitive, interesting truss, the key to getting there is to take a look at that diagram and say, where is the force? Why did it change? And follow the force either from your reaction nodes upwards or from your load node downwards and say, how is that being distributed in the structure? How am I affecting the length of those members? Can I make them shorter? If I make them shorter, do they become strong faster than the load goes up? Because their load will go up as you make them tilt downwards. Okay, so I would suggest that if you've taken a look at Fusion 360, that's great. It also does an amazing job, hugely complex buckling analysis, but going through and doing that editing process can take a lot of time. With just some simple hand tools and a calculator, simple hand tools, calculator and a pencil, right? Now, you can sit down and do some pretty quick calculations, or JFMatrix, it's a pretty simple tool too. And then you can get your design roughed out, put it into AutoCAD, take it over to Fusion 360, and see what Fusion 360 says, then cut it out on the laser, see if Fusion 360 matches your results, record a video of your structure failing so you can see which part fails first. That part is going to need to be reinforced. See if it matches what Fusion 360 predicted, and see if it matches what you're seeing coming out of JFMatrix too. So a few simple analyses will help you simplify your truss. This is not about slapping as many nodes as you can. Okay, nodes cost time and they cost you weight. So just like in West Point Bridge Designer, you'll recall each time you added a node or a member, you got penalized with some additional cost in there. You really want to boil this structure down to something simple. It's possible. I'm not sure. I don't think the strongest truss that we see is only going to have 4 nodes in it. I'm thinking maybe 6 to 7 nodes. I doubt the strongest truss will have more than 10 nodes to it. I'm not 100% sure on that, but I know my instinct for designing is going to be to try to keep it simple and get my lengths and cross-sectional areas optimized more than going and designing something with a whole bunch of members in there. We just don't have enough time to do the iterative design necessary to come up with something hugely complex. So that's what I want to take a look at today. There was one final analysis I think I did right on here. So I'd been at this one right in here, and we took a look at this result right here. Oops, there's the that was what I was looking for right here. We just taken a look at this one right here, and we talked about these being zero force members. Then we came over here and we had that node up at the top. I brought it right down here so that I had a flat section right up at the top, and now I've got another zero force member right in here. Now the reason this is a zero force member, of course, is because this is a perfectly flat line, and a perfectly flat line, okay, perfectly horizontal, can't support any vertical component. So if this member here were to pull down on this one at all, those two would just collapse because there's no vertical support going into right there. Um, so this member is probably not helping us out all that much. If you wanted to do this design, you could probably, well, you don't want to get rid of that node right in there because then you'd have this hugely long compressive member right up here. But one thing I do like about this structure when it comes down like that is I'm seeing like 8 newtons in compression. It drops off quite a bit over here. I'm thinking with that 8 newtons in compression um, running right along here, that's a nice even force in each member. So you can make each one of those um, subject to about the same load. Now we do want to take a look right in here, and yeah, that should be a 70 millimeter distance right between there and there, because this is 150. That's probably 75 from there to there, so we're good. You could bring this down a bit more. You can bring this one down a bit more. You know, what happens if we take this, unlock the structure, come in here and edit this node right there. So edit, um, edit joint coordinates for that node right there. I am going to bring it down a bit to 1.15, and I'm going to move it over just a hair to 2, put it at the halfway point. Okay, and I'm going to bring this one down a little bit, 1.25, and I'm going to bring it in a little bit to 4.75, exactly halfway right in there. Okay, I'm going to run my analysis on here, and now sometimes when I do this, it's hard to see those numbers. I think you have to, if you don't see the numbers showing up right in there, that's because it's displaying them in red on a red number. Over here, you can see it's doing red. Sometimes it does white, sometimes it does red. You can get the results in the reports right down here. And like I say, you can get the links, beam loads right in here, and somewhere down here, analysis results. Here you go, your axial loading for each member is going to be right in here, so you can pull that out. Okay, folks, so Fusion 360 is really cool. It can do really, really complex analyses. In fact, right now, I'm playing around with something I haven't done before in Fusion 360 called generative design, where I tried setting it up and I said, okay, here's the conditions, here's the constraints. You can have material within this range, remove things and make it as light as possible. And it goes through and it generates pretty cool organic looking structure. I didn't have any way to tell it that it had to be a truss with 70 millimeters between nodes, but I just wanted to see where it was going to put all of the material. And you can see it's still processing this. It's not done yet. It's been running for a couple hours now. But right down here, it's this is my lightly loaded end, and it's got much less material on that side, much more material right down on this side. And it actually looks like it flattens out along the top right there, whether that's because of the height constraints I set for it or not. It's going pretty tall. So I don't think that's going to be a useful result. Now, this is part of your computer analyses. You have to know before you go and ask the question on the computer what to expect. This is not the answer that oh no, it's not done processing yet. It's still working on that. So I'm going to let that run. Thank you, Autodesk. Your servers are doing yeoman's duty coming out with an answer that I am probably going to completely ignore because I didn't set the problem up exactly the way they needed it, and garbage in, garbage out. But as far as JFMatrix goes, it's simple, it's straightforward. You could, if you wanted, sit down and solve this problem by hand with a calculator. Okay, it's not. You run into a couple of problems right here. I haven't shown you how to start out where you've got multiple members supporting a node right here. That would be a little bit fussy to do. But you can do it with a little bit more advanced math than we've done. JFMatrix takes care of it quickly and easily for you and lets you visualize those forces. Keep your trusses fairly simple, fairly straightforward, and think about where the forces are going to be flowing. Okay, looking forward to your questions on this, and looking forward to seeing the trusses as we start cutting them out and trying out the new truss testing jig with them.